So our next speaker is from Andra. It's Denise Ricard, who's going to talk to us about the Chance programme and the characterization of conditioned nuclear waste for its safe disposal in Europe. Thank you.
Good morning, ladies and gentlemen. So I will talk about the Chance project. That is about the characterization of conditioned nuclear waste for safe disposal in Europe. So here we have some general information about the project. So this project is funded by EURADWASTE Research and Training Program 2014-2018. It's a project of 4 years. It started in 1st of June 2017 and it will finish in the end of May 2021. So the total Chance budget, it's around 4 million euros, and we have 12 partners from 8 European countries participating to the consortium. So here we have all partners from the project. So partners come from France, Belgium, UK, Romania, Poland, and Germany. So the Chance project has 2 main objectives. The first one is to produce a comprehensive understanding about the conditioned radioactive waste characterization and control scheme employed in Europe today. And this work is based in inputs from the end users organizations, coming from different waste management organizations, from waste producers organization and repository operators. So the second objective of the project is to test, develop and validate non-destructive techniques for the improvement of the characterization of conditioned radioactive waste. And we focus our development in 3 innovative techniques: the calorimetry, that it's used to reduce uncertainties to the inventory of radionuclides; the tomography, that's used to the control of large volume of nuclear waste; and the cavity window spectroscopy, the CRDS, it is used to characterize outgassings of radioactive wastes. So here we have the structure of the project. So we have a 6 work package. The first one, it's about the management and coordination. The work package 2, it's about methodology. So in this work package, we'll produce an overview about the current and conditioned radioactive waste characterization quality control, and also try to identify R&D needs in this field. Work package 3, 4, and 5 are about experimental development. So work package 3 is about the calorimetry, work package 4 about the Moon tomography, and work package 5 about the CRDS, and work package 6 is about dissemination and training. So now I will present the objectives of each work package and the results after 2 years of the project. So here for work package 2. So the main objectives of this work package is to identify current methodologies and shortcomings for the characterization of conditioned radioactive waste in Europe. So particularly we try to identify the key parameters that need the characterization, the technologies that are commonly used today in Europe, the problematic issues about the characterization, and also try to identify technology gaps in this field. So all this, to get this information, so we asked some contributions for our end users group. We have questions about the characterization, different subjects about the characterization of radioactive waste. So some results for this work package. So first of all, we prepared a questionnaire to obtain an overview about the characterization of conditioned radioactive waste. So we had 18 questions in this questionnaire, and we have questions also about the waste acceptance criteria, the methods currently used, special issues, etc. But we have also questions related to work package 6 about the social, technical, and ethical concerns. So this questionnaire is a deliverable for the project, so it's available in the website of Chance. So if you're interested about that, please go to our website. And so after preparation of this questionnaire, we send it to our end users members. And we receive 13 answers, 30 questionnaire answers. And so we analyze these answers, and we prepared a report that it's under finalization and will be available soon in the website of Chance. So we present some results, and I'll talk about all because we have a lot of information. So just some subjects. So concerning the identification of waste acceptance criteria, so we can see that the waste acceptance criteria depend, of course, on the disposal or storage considering, and also depending on the country, we consider it, but despite the difference, we could define 4 groups of parameters that will define the waste acceptance criteria. So we define the criteria radiological parameters, chemical parameters, mechanical parameters, and other parameters. So concerning radiological parameters, what is important is the radionuclide activity, per waste packages, the dose rate, the surface contamination, content of fissile materials, and for some disposal, it's also important to have the heating power. Concerning chemical parameters, so it's important to have information about inventory of toxical species, complexing and chelate agents, and for some disposals, we have some limitations in the content of, for example, of organic substance or pyrophoric flammable materials. For mechanical parameters, we can see the compression resistance, the drop resistance, but also there are some parameters that are related to the behavior of the matrix, such as the swelling of the matrix or diffusibility. For the other parameters, you can see the hydrogen from production by corrosion or hydrolysis, the homogeneity of the waste, and also some parameters related to the disposal container, such as the physical dimensions and waste. So now concerning the problematic issues for the characterization of conditional radioactive waste. So we had a lot of answer for these issues, but it seems that the most important problematic issue is the characterization of conditional legacy or historical wastes. And there's particularly difficult to determine the radiological parameters and also to identify the materials that are present in the waste packages. There are others important problematic issues such as the determination of alpha and beta activities in conditioned radioactive wastes, because we have attenuation of cyanide mainly for waste packages where when we have compact wastes or waste or packages where we have concrete. Other difficulties are the traceability of chemical content of waste packages. So some difficulties for the sampling of materials, and difficulties associated to the monitoring of waste packages already storage in facilities. So this is just some results, and we have soon all results in our report in our website. So now I go to work package 3. So the main objectives of the work package is to test and evaluate the performance of a calorimetry for inventory of radionuclides, and also to identify how we can couple the calorimetry to other techniques, such as the gamma spectrometry or neutron passive measurements, and also to do some studies about the certitudes of the calorimeter results and other non-destructive techniques that will be coupled to the calorimeter. So in order to get these objectives, we are building a calorimeter of 2,000 liters. So it's being designed and built by CAP Technologies. And also after we have an experimental program that will be carried out on mock-up drums, and maybe in the end of the project we try to do some measurements in real drums. So now some results of this work package. So a first report was produced about the applicability of the calorimeter to real waste characterization. So this deliverable is also available in our site. So in this report, we have an overview of a non-destructive analysis. So we're talking about gamma methods, neutron methods, and of course, calorimetric methods. We have some modelization, Monte Carlo modelization about the calorimeter, and some evaluation of the effect of gamma energy and neutral deposition in the calorimeter and in the system. So just some information about the applicability of the calorimeter. So the calorimeter is adapted to measure alpha and beta emitters, but it cannot discriminate or locate the heat source, and it's complementary to other techniques such as the gamma and neutron spectroscopy. So now some results about the construction of the calorimeter. So we are building a calorimeter of 2,000 liters, and the range, it's a range of detection is from 10 to 3,000 milliwatts. So it will have optimized a lower detection limit, what about 1.5 milliwatts. So here we have some images of the calorimeter. So here we have an illustration. So it's a calorimeter that is open in 2 half shells. And so here we will put the drum, and we have the ghost reference underneath the drum. And so here there are some recent pictures of the calorimeter, so in the position, open position, and the closed position. It's a quite big equipment. It has around 5 meters length and 2 by 2 meters height. And so we are finishing the commissioning of this equipment is almost finalized, and we will start the measurements in the next summer. We will start the measurements with the mock-up drums. So, and after we have some modelization about the results of the calorimeter. So now talk about work package 4. So the work package 4 concerns the development of a mobile moon tomography instrumentation to image large volume and heterogeneous waste packages. So the specific objective of this work package is to build a suitable mobile moon detection system, and after image real waste drums, and do some studies about the performance of the technique. So just some words about the moon particles. So the moon particles are occurring naturally and are produced when cosmic radiations enters in atmosphere, Earth's atmosphere, and so we can use the moon to image dense materials. So now some results about our package 4. So the detector system is being commissioned. So here we have a recent image of the system. So it's quite big equipment. It has 3.2 meters of length and 2.5 for height. And so as you can see, the detector system is composed by 2 parts. The upper part, so we will detect the moon particles that arrive in the system, and then above the samples. So here we will put the drums or other samples, and then after we will have the detection of the scattered moon particles. So we have done a lot of modelization about the system. So for the moment, we can identify uranium cuboids embedded in concrete. We can distinguish between cuboids of uranium, tungsten, and lead. We can also distinguish voids or gas bubbles in the matrix. And so now the commissioning is almost finished. We started now with the measurement. First we do measurements with simple samples. And then we imagine mock-up drums, and maybe we're trying to imagine real drums, and namely castor drums with high zeta materials. So here just some images for the modelization of, for example, in the top of the image, we have modelization of uranium block embedded in concrete and in a waste container of steel. So the uranium has a diameter of 10 centimeter, and different resolution is obtained considering the modelization or algorithms that they are using. In the bottom of the figure, we have some images of lead and steel. So we can see that the resolution will depend on the size of the sample and also the density of the material. For work package 4 now, the main objectives is to advance the use of cavity ring down spectroscopy, CRDS. And so there are two distinct objectives in this work package. The first one is to develop a new instrumentation for detection of the chloride 36. And the second one is to demonstrate the application of the technique to measure C14 outgassing. So some results for this work package. So concerning the development of a CRDS for the chloride 36 measurement. So first of all, we had done some modelization to identify a suitable absorption line for hydrogen chloride 36. So here in the figure, we have the position of all hydrogen chloride isotopes, and so the line of hydrogen chloride 36 is located between hydrogen chloride 35 and hydrogen chloride 37. Concerning the measurements of C14, so we started with a measurement of outgassing of CO2 from non-irradiated graphite. And so we have seen the behavior when we heated the graphite to 150 degrees. And now we started the measurements to irradiated graphite. So finish with some information about dissemination and training. So the main objectives of this work package is to integrate, communicate, the dissemination of chance results. So of course they are in charge of the communication of the project, but also they do some studies about the socio-technical concerns. They are also in charge of education, training and education of young professionals, and they will synthesize all results of chance in the end of projects. Just some words concerning the education of young professionals. So we have the Chance Mobility Fund that is open for young professionals. So the students, PhD students and junior professionals can apply to have to do internships, test preparations, or scientific visits hosted by a partner of a Chance project, or to participate in conferences and workshops. And I will finish with some communication tools. So we have a public website, we talked several times. So in this website, we have the news about the project, the events, public deliverables, and publications. We will organize also the training courses towards the end of the Chance projects. And now, so just some words about the topical day that was organized by the SKCUN last March in Michelin in Belgium. So it was a meeting of 2 days. So the first day we had a conference, a seminar about the non-destructive analysis techniques used to characterization of conditioned radioactive waste. And the second days, we had a visit of Bego process facilities. So we had a lot of people coming to this day, and also had some people that would look at the presentation on live streaming during this session. So we are happy to have so many people interested by chance. So it's all. I thank you very much for your attention.
Thank you, Denise. Some real state-of-the-art technology there with some excellent application to industry.